So today I wanted to talk about um, total response of general second order circuits. So before we're able to do this, we're going to have to go back and look at series RLC circuits and parallel RLC circuits very briefly to see if we can kind of tease something out. So in a parallel RLC circuit, we had a situation that looked something akin to this. I believe this is how I derived it for the most part. I had some source IS, bless you. I had a switch actuating at T is equal to 0. This was terminal A, this was terminal B. Here I had my resistor R, my inductor L, and my capacitor C. I defined a voltage V across all of my elements. I'm just going to move that L to the other side so it doesn't get in the way. And then I said that this was IC, this guy was IL, and this guy was IR, like so. And I applied Kirchhoff's current law to find that IR, let me do it this way, plus IL plus IC was equal to 0. I substituted in relationships only in terms of that voltage V that was common to everything. So that was, let's see, 1 over R times V plus, let's see, C dV by dt plus 1 over L times the integral from T naught to T of V T prime dt prime plus IL at T naught. I integrated both sides, took the derivative of both sides of this thing, and then I divided through by a factor of C, which left me with the second derivative of the voltage with respect to time plus 1 over RC times the first derivative of the voltage with respect to time plus 1 over LC times the 0th derivative, as I like to call it, just the function itself of the voltage with respect to time. And this was equal to 0. So if we look at a parallel RLC circuit, we defined alpha, our Neper coefficient, to be 1 over twice RC. And similarly, we defined omega naught to be the square root of 1 over LC, right? Well, what are the relations of those two coefficients to, or those two constants to the coefficients of our differential equation here? Well, it looks to me like this guy right here. I'm going to call it B, since it is the coefficient on the first derivative term, is just equal to, let's see, 1/2 times alpha. So if I took, actually, the other way around, twice alpha. Thank you for that. Or expressed another way, we could say that alpha is just this coefficient b from our second order differential equation divided by a factor of 2. And pretty similarly, this guy right here, which I'm going to call lowercase c, looks to just be omega naught squared. So I could say that omega naught is just the square root of whatever that coefficient lowercase c is. Okay. So now let's look at a series RLC circuit really quickly. So in a series RLC circuit, we might have something like this. So here is, actually, let me remember ballpark how I did it. I know over here I had an R and an L and my capacitor. I had a switch doing something like this, if I'm remembering correctly. And then over here might have been my voltage source or current source, where this was my current I of t. Here's my voltage VR, my voltage VL, and my voltage VC, like so. If I applied Kirchhoff's voltage law around this loop, I found that VR plus VL plus VC were equal to 0. Substituting things in terms of that common current I had R times I of t plus L di by dt plus 1 over c times the integral from t naught to t of I of t prime dt prime plus v c at t naught was equal to 0. And once again, I took the derivative of both sides, and I'm dividing through by a factor of L in this case to get a second order differential equation that looks like the second derivative of our current with respect to time plus R over L times the first derivative of our current with respect to time plus 1 over LC times the integral. Actually, no, I won't have an integral anymore. Sorry, that'll be just my current with respect to time is equal to 0. And we found that for a series RLC circuit, alpha was equal to R over 2L, and omega naught was once again equal to 1 over the square root of, square root of 1 over LC. So this guy right here, my coefficient beta, is once again exactly twice my Neper coefficient alpha. So we could see that alpha is just b over 2. And my coefficient here, c, is once again just omega naught squared. So that I could say omega naught is just the square root of whatever that coefficient is in that second order differential equation. So it doesn't matter whether or not we have a series RLC circuit or a parallel RLC circuit. If I can write a second order differential equation for that system, and I can solve for the coefficients of that second order differential equation, that will allow me to calculate what my Neper frequency is and what my resonant frequency is. And then from there, I can treat it just like anything else. When alpha is greater than omega naught, I have an overdamped system. When alpha is equal to omega naught, I have a critically damped system. When alpha is less than omega naught, I have an underdamped system, and so on and so forth. So this is the approach that we're going to take for our general RLC circuits that don't easily fit into the bucket of a parallel RLC circuit or a series RLC circuit. So let's take a look at such a problem, okay? So let's say that I have the following system. So I've got some voltage source here, Vs, connected to a switch that is going to close at t is equal to 0. I'm going to have some resistance here, which I'm just going to call R1 for right now. Let's put an inductor here, L. Let's put a second resistor here, R2. And let's put a capacitor here, C. So this is an example of a circuit that isn't going to be a parallel RLC circuit or a series RLC circuit. Okay, we can see that it's pretty close, but during the transient condition with my system off, my circuit essentially looks like this. So here's R1. Here's my inductor. And then here's R2 and my capacitor. So it's really close to a parallel RLC circuit, except that that resistor R2 there is messing things up. So what we're going to have to do is write a second order differential equation for this system and then solve for those coefficients alpha and omega naught based on what the coefficients of that second order differential equation are to understand how it's going to behave. Okay. So generally speaking, we're going to have to use some combination of Kirchhoff's voltage law. Oh, goodness. How did the whole page go away? I've literally never had that happen before. Edit, undo. It did not. Okay, it's back now for the most part. Please stay on the page. Okay. So we're going to have to apply some combination of Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law and things like that to this guy. We can, technically speaking, apply mesh analysis or nodal analysis or something like that to one of these systems. And it will work, but I usually find that that is going to be more of a pain in the ass than it's worth than just going through KCL and KVL. So that's what I'm going to show you guys how to do. And for what it's worth, we're only going to use this for second order systems because once we get to, third order systems where we have 3 independent energy storage elements, the math gets so convoluted that we're actually going to wind up using what's called the Laplace transform. For those of you that have had Math 245, you know what that is. For those of you who haven't had Laplace transform or Math 245, something you'll learn pretty soon. But that's how we're going to cover third order and higher circuits because this is the limit for the math not being utterly terrible. Okay. So what I'm going to do here is I'm going to simply define my capacitor currents and voltages and my inductor currents and voltages, and then we're going to just kind of go from there, right? So this might be the voltage drop across my inductor VL of t. This will be my inductor current IL of t. This will be the voltage drop across my capacitor VC of t, and this will be the current flowing through my capacitor IC of t, like so. So what I'm going to do here first is I'm going to choose to write a KVL equation around that right-hand loop, okay? So let me just put a note here, KVL at right-hand loop. And so looking at this guy, I might say that the voltage drop across my inductor, so VL of t is going to be equal to the voltage drop across that capacitor R2, which could be expressed as R2 times IC of t, plus the voltage drop across that capacitor, BC of t. Does anybody have any questions, comments, or concerns about this relationship? Okay. Now, what I would do, because my ultimate goal here is to get a second order differential equation either in terms of IL of t or VC of t, is I'm going to choose to express my inductor voltage in terms of my inductor current, and I'm going to choose to express my capacitor current in terms of my inductor voltage. So that might look something like, here's L times D IL by dt is equal to R2, let's see, capacitor current is C dV by dt. So R2 times C times the derivative of my capacitor voltage with respect to time plus my capacitor voltage with respect to time, like so. Okay. I'm going to put a pin in this equation because there's not really anything else that we can do to it. But notice all of our terms are expressed as either functions of inductor current or capacitor voltage, okay? So what I might do now is write a KCL equation, okay? So I'm going to write a KCL equation at this node right here. So I have a current that's flowing in that is going to be, so let me just put KCL at top middle node. So my current that's flowing in is going to be VS minus VL of t divided by R1 will be equal to the sum of the inductor current and the capacitor current. Current flowing into that node equals the current flowing out. So before I start messing around with this guy, does anybody have any questions, comments, or concerns? So once again, I'm going to wind up expressing that inductor voltage in terms of the inductor current and the capacitor current in terms of the capacitor voltage. And so what that's going to leave me with, oh goodness. That is something akin to this. So I might have VS over R1 minus, let's see, so voltage drop across an inductor is LDI, so that's going to be L over R1 times the derivative of my inductor current with respect to time is equal to IL of t plus C dV by dt, like so. So now I need to think about this guy for just a moment because I have these two equations. Let me just put a number by this one really quickly. So here's number one, and here's number two. And I have to figure out a way to essentially manipulate these guys to express everything only in terms of my inductor current or only in terms of my capacitor voltage. So let's look here at this guy that I have labeled as equation one, and let's manipulate it. I think it's going to be the easier one to do. So actually, maybe not. So my initial inclination was to essentially solve for VC here, which would have given me, VC is equal to L di by dt minus R2 times C times the derivative of my voltage. And then I could take the derivative of that guy and I'd wind up getting my an expression for dc by dt. But if I substitute that in, I think I'm still going to be missing something. So let's just look at this and see what happens here. So I could say that VC of t is equal to L di by dt plus R2C dV by dt minus, thank you. If I take the derivative of 1, with respect to t, I would get dVc by dt is equal to L times the second derivative of IL with respect to time minus R2C times the second derivative of the voltage with respect to time. And my concern is that if I were to substitute this whole thing in to right here, I still don't have everything explicitly in terms of my inductor current because I still have a capacitor term. So what I'm thinking about now is manipulating equation 2. Okay. I'm trying to avoid getting into a circular reasoning system here. I think if there's just some other super obvious relationship that I can use, but I don't think there is. All right, let me see what happens if I play around with relationship 2 just really quickly. So moving things around, I could say that C dv by dt is equal to Vs over R1 minus L over R1 times the first derivative of my inductor current with respect to time minus IL of t. Did I algebra that correctly? If I plug 2 revisited into this guy right here, let's call this 3 for what it's worth. So substituting 3 into 1, this is, I would have Vc of t is equal to L DIL with respect to time minus R2 times C times the derivative of my voltage, right? Where that would be Vs over R1 minus L over R1 DIL by dt minus IL of t. Let's call this guy 4 for right now. And goodness gracious. So I don't want to use VL literally ever. I only want things in terms of IL and VC. Well, so if we go back to what we had here, I had essentially here, when I had a series RLC circuit, or excuse me, a parallel RLC circuit, I had a second order equation where everything was in terms of only the capacitor voltage. And down here, when I had a series RLC circuit, I had a second order differential equation where everything was in terms of the inductor current. I'm going to wind up with one of those situations. Actually, what you'll find if you work this and manipulate things long enough, you'll wind up getting, you can get a second order differential equation in terms of a capacitor voltage and a second order differential equation in terms of the inductor current, and they're both going to have the same coefficients. So whatever way the math makes easier is the differential equation that you should wind up doing. My only problem here is that neither way seems particularly easy at the moment. And I have to be overlooking something incredibly simple. So are you talking about right here? No. So the current that's flowing in, which is this guy right here, So that's the current flowing into this node is equal to the current flowing out, where IL is defined as flowing out and IC is flowing out. So those should definitely both be positive. So yeah, because it's flowing in is equal to out, it should be VS minus VL. So let me think here. So I have an expression for VC of t down here that I have as equation 4. I'm going to take the derivative of this guy, and I'm going to hope that not everything cancels each other out in just a moment. Okay. So the derivative of the capacitor voltage with respect to time is going to be L times the second derivative of my inductor current with respect to time. That first term right there is going to be a constant, right? So when I take the derivative of that, nothing's going to happen. That minus sign is going to cancel each other out. So I'm going to wind up with a plus R2L over R1. That's going to be a second derivative relationship as well. And then plus R2 times IL of t, and I might just lump some things together here. So that's going to look like L times 1 plus R2 over R1, second derivative of my inductor current with respect to time, plus R2 times, oh, actually, I was taking the derivative of this thing, so that should be so let me just, excuse me, double check the math here. So taking the derivative of each of these terms. So the derivative of the capacitor voltage with respect to time is just dV by dt. Then I take the derivative of this first derivative term with respect to time, which is giving me a second derivative. I'm distributing this negative sign through, so I think an easier way to do that would be, no, I'll just leave that as is for right now. So I'm taking the derivative of this guy right here, which is a constant, so it's 0. That's why it's not getting rewritten. I'm taking the derivative of the next term, so that's where I'm getting a plus R2 over R1 times L times the second derivative. Then I'm taking the derivative of the last term, so I have minus times minus is plus R2 times the derivative of IL with respect to time, and then I just lump those like terms together. So if I call this guy right here 5, let's see what happens if I substitute 4 and 5 way back into this one. Okay. Yes.
I was gonna ask why we had L times one plus R2 over R1 for the term of L.
Yeah. So I just wanted to lump that stuff together because ultimately I want my second order differential equation to have a constant coefficient or a coefficient of 1. So in 2 to 3 steps, if this works out the way I hope it does, I say I hope it does, and I think it does because I'm genuinely concerned right now. I'll wind up dividing through by that thing in order to sort some stuff out. So anyway, let's see. So I have an expression for VC that is only in terms of inductor current. I have an expression for the derivative of the capacitor voltage that is only in terms of the inductor current. And I have this equation up here where I have inductor current by itself, or an inductor current term by itself, and then something related to the derivative of the capacitance, which I now have expressed only in terms of the inductor current, and the capacitance voltage itself, which again, I've expressed only in terms of that inductor current. So let's see what happens if we substitute into one. So I'm just going to rewrite one real quickly. So that was L di by dt was equal to R2 times C times the derivative of the capacitor voltage with respect to time plus VC, if my memory serves me correctly. That seems legit. So now I'm going to have R2 times C multiplied by L times 1 plus R2 over R1, the second derivative with respect to time, plus an R2 times the first derivative with respect to time. And I'm going to do this on a second line because I'm running kind of out of room here. Plus L di by dt minus R2 over R1 times Vs plus L times R2 over R1 times my first derivative plus R2 times IL of t. So I have something that appears to be expressed entirely in terms of my inductor current, which is what I was aiming for. Now I just have to make sure that it doesn't all cancel itself out. Josh.
So are we trying to get like equations in terms of both the inductor current and the capacitor current?
No. So we want a single equation that is a second order differential equation that only has inductor current or only has capacitor voltage. And I believe we are essentially there, right?
Okay.
So let's keep on looking at this guy and then we'll see what happens. So
is that specific for the type of circuit we're analyzing, or is that across for the general order?
So for a general RLC circuit that is not a series RLC circuit or a parallel RLC circuit, our ultimate goal is to get a second order differential equation only in terms of capacitor voltage or only in terms of inductor current. Okay. So I think, so I have an positive L times DIL by dt term on the left-hand side, and I have that same thing right here. So those guys cancel each other out. I could just subtract that from both sides, okay? What I'm going to do now is I'm going to move that constant term of R2 over R1 times Vs to the other side of the equal sign. So I'll have R2 over R1 times Vs is equal to, and now I want just my, let's see the second derivative term first, right? So I've got an R2 times a C times an L. So I'm just going to write this as R2 LC 1 plus R2 over R1 times my second derivative of my inductor current. So just to be clear, that's taking care of this guy right here, right? For my first derivative, I have an R2 by itself. Then I also have this term right here. So that's going to be R2 plus L times R2 over R1 times my first derivative. So that's taking care of this guy right here and this guy right here.
R2, should it be R2 squared times C?
You know what? You're absolutely right, because I forgot to take in that R2 squared times C. Yes. And the units would have messed things up, but thank you for catching that. You're 100% right. I forgot to just, goodness gracious, distribute that R2 times C that was out to the left. So thank you for that. And then I believe the only thing that's left here is just an R2 times IL. If I algebraed this thing correctly, which at this moment is highly suspect. So the next thing that I would do is divide both sides through by that factor of R2 LC multiplied by 1 plus R2 over R1. And so that would look something like this. So R2 over R1 times Vs divided by R2 LC 1 plus R2 over R1 is equal to the second derivative of my inductor current plus R2 squared C plus L R2 over R1 all over R2 LC times 1 plus R2 over R1 times the first derivative of my inductor current plus R2 divided by R2 LC 1 plus R2 over R1 times my inductor current by itself. It will. So you mean specifically here and here?
Yes.
Sure. Why the hell not? So from this horrifying thing, we can see that the Nepper frequency for this guy is just going to be 1/2 times that thing, right? So R2 squared C plus L R2 over R1 divided by R2 LC times 1 plus R2 over R1. And omega naught is going to be the square root of the coefficient on the 0th derivative term. That's going to be the square root of 1 over LC times 1 plus R2 over R1. So we did a lot of things here, okay? Several opportunities for us to have made mistakes, and by us, I mean goodness gracious, mostly me at this point. So I probably want to check this. Yes.
So, if we wanna get our coefficient for a second derivative, to one, why do we keep that one at 12?
To make it match everything that we did earlier. So if we scroll up here, the coefficient for our second derivative term was 1, and that's what allowed us to define alpha. And similar alpha and omega naught. Similarly, same thing here. So having that coefficient of the second order term as 1 keeps our alpha and omega naught relationships the same for everything.
Is alpha and omega for only this specific design?
Yes, for this very specific circuit. So for every circuit that we get that isn't a series RLC circuit or a parallel RLC circuit, you will have to come up with your own second order differential equation for them, which is by far the hardest part of this. Once you do all of this horrifying stuff, it is exactly the same as everything else we've done. So let's look down here. I know, and again, I would not be remotely surprised that I made a mistake somewhere in here, but I want to find out. So what I'm going to do is I'm just going to say, let R1 equal R2 equal L equal C is equal to 1, whatever. So 1 ohm, 1 farad, 1 Henry as is appropriate. And so that means that we would have alpha is equal to 1/2 times a factor of, let's see, so that's 1 plus 1 is 2 over 1 times 2. Did my mental math work out there correctly? If I put 1 in for everything, I think 1 squared times 1 is 1. And then or 1 times 1 over 1 is also 1. And then I add those two ones together. So that looks like a 2 in the numerator to me. 1 times 1 times 1 is still 1, multiplied by 1 plus 1. So that's 1 times 2. Yeah. Omega naught is going to be the square root of 1. So that's 1, and then that's 2. So just the square root of 1/2. So I think in this case, alpha is greater than omega naught. So this is an an overdamped system. So we'll use that in a minute. Okay. So at t is equal to 0 minus, let's just scroll up here real quick and look at things. At t is equal to 0 minus my voltage source, and let's call that a 1 volt source as well, just for the hell of it. My voltage source is disconnected, so everything is 0. Everybody okay with that? At T is equal to 0 plus, now my voltage source is connected. So here's my 1 volt voltage source. Here's a 1 ohm resistor. My inductor is going to look like an open circuit. Here's a second 1 ohm resistor. My capacitor is going to look like a short circuit. Let's see. So this is IC of 0 plus. This is VC of 0 plus. This is VL of 0 plus. This is IL of 0 plus. So we know that VC at 0 plus has to equal VC at 0 minus, which was 0 volts. We know that IL at 0 plus has to equal IL at 0 minus, which was 0 amps. I think I could say that IC at 0 plus is just 1 volt over 2 ohms is half an amp. And pretty similarly, I can say that VL at 0 plus is just going to be 1/2 of 1 volt using voltage division is half a volt. Everybody okay with that analysis? At T is equal to infinity, our switch is still closed. So here's our 1 volt source, our 1 ohm resistor, our inductor is now a short. Our capacitor is now an open. So here's IC at infinity, VC at infinity, VL at infinity, IL at infinity. Pretty obviously, IC at infinity is 0 amps. VL at infinity is 0 volts. I think IL at infinity is going to be 1 volt over 1 ohm is 1 amp. And VC at infinity, I believe, is 0 volts by inspection, but let me explain my logic there. No current flows through the 1 ohm resistor on the right, which means there's no voltage drop across the 1 ohm resistor on the right. So VL at infinity and VC at infinity should be the same thing, since positive polarity is on top for both and negative polarity is on bottom for both. Yes.
Would that be different if there was like, a resistor in series with the inductor?
Yeah. It actually probably would have made this easier. But I didn't think that far ahead, quite obviously. So, all right. So S1 for this system, because we found that it was overdamped, is negative alpha plus the square root of alpha squared minus omega naught squared, right? Alpha is 1/2, if I'm remembering correctly, and omega naught is just the square root of 1/2. So negative 0.5 plus the square root of 0.5 squared minus the square root of 1/2 squared. I'm an idiot. Square root of 1/2 is greater than 1/2. Square root of 1/2 is square root of 2 over 2, which is 0.7 and some change. So I just looked at that and said the square root was smaller. So this is actually an underdamped system. I'm just dumb. Let me go all the way back. throw that in your calculator just to make sure I'm not losing my mind more so than usual, but square root of 1/2, I believe is 0.707. It is indeed. So omega naught is greater than alpha, gives me underdamped. So that's actually not what I want down here. Omega d is the thing that I need. So that's the square root of omega naught squared minus alpha squared. I was terrified that I was going to get a complex number. I did, and I remembered why it happened was just me being bad at math today. Somebody else throw that in their calculator, make sure I didn't manage to screw this up too, please. Okay, so we have an underdamped system, and an underdamped system, so we're going to say that IL is B1 cosine omega dt plus B2 sine omega dt, all of that e to the minus alpha t plus IL at infinity. Evaluating this at t is equal to 0 plus, only thing that's going to survive this whole thing is B1. And so I could say that B1 is going to be equal to IL at 0 plus minus IL at infinity. IL at 0 plus was 0 amps. IL at infinity is 1 amp, so B1 is negative 1 amp. VL of t is going to be L di by dt, which is going to look like L times, I'm gonna borrow your table again. Omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt e to the minus alpha t. And so VL at 0 plus is going to look like L times omega d B2 minus alpha B1, and all of the other terms are going to go to either 0 or 1. So that's the only thing that survives there. We're trying to solve for B2 since we already know what B1 is. So I'm going to try to algebra this thing out. So VL 0 plus L times alpha times B1, all divided by L times omega d is equal to B2. If I algebraed that correctly. Did I algebra that correctly? People whose brains are functioning. I'm getting a thumbs up. Good deal. So if I substitute in numbers there, so VL at 0 plus was half, I think. Where'd it go? Yeah. So 0.5 plus 1, alpha was 1/2, B1 was -1, all over 1 times 1/2. I believe this comes out to be 0. Yeah. And from this, we 2, because omega d came out to be 1/2. So from this, we could say that IL as a function of time is -1 cosine 0.5t e to the minus alpha was also 1/2, if I'm remembering correctly. 0.5t plus 1 amp. Okay, let's simulate this and see how horribly wrong I got it. Oh, right here. Thank you.
I have a question about the general approach to these.
Sure.
Well, is it a good practice to always just do IL of T for your, I guess, main equation, so it's the derivative and go for V of T?
So
That's what I've noticed kind of works the best. On the homework at least.
it depends on what I'm asking for. So in this particular problem, I was just solving for IL here specifically because our differential equation was in terms of IL, but I could have used, so let me just go back up here. When we calculated this alpha and this omega naught, if we had somehow managed to do even more horrifying math and get this differential equation in terms of our capacitor voltage, we would get the exact same alpha and the exact same omega naught. I just chose to run with using IL just because I wanted to be able to do something quickly because I know what time it is and I want us to simulate it and see whether or not this process was correct. So that's why I didn't do the capacitor, or excuse me, the inductor voltage. That would just be more time. Me choosing to do my IL to set up my system was just a binary decision. It was either going to be IL or VC, and I just chose IL just for the hell of it. Yeah. Yep. No. If there is literally any change to this circuit, you will get a different value of alpha and a different value of omega naught. Yeah. So let's see, let's try to throw this in here really quickly. So this was a 1-volt source during the transient condition. Then I had, actually, that's going to be a 1 ohm resistor. That's going to be a 1 ohm resistor. That was a 1 Henry inductor. Over here is going to be a 1 farad capacitor. I'm going to just wire all this stuff up real quick like. I will be utterly amazed if I didn't somehow screw up all of that horrible algebra and stuff at the beginning, but you know, there is a chance that I actually did this right. I legitimately don't know why this was so much harder than putting the resistor in series with the inductor. But for whatever reason, that just made the math real gross. Somebody's phone sounds like it's vibrating. One, one. PC, meant for that to be capitalized, but it's fine. Initial conditions on both things were just 0, if I'm remembering correctly. And let's run this for 3 seconds arbitrarily. Here's my inductor current. Not quite settling to 1 amp like I would expect, so let me just change that to 5 seconds or so. Now it looks like it's okay. So it did overshoot the final value, which is a good indication that it is actually underdamped. So we might be amazed. I'm going to add a trace. So if I'm not mistaken, this was -1 times the cosine of 0.5 times 180 over pi times time multiplied by exp of -0.5 times time. Oh, I'm missing a parentheses there, I believe. Holy shit. Sorry. Oh, it's shifted down 1, but I forgot to do the +1 at the end here. Plus y at infinity. Yep. Somehow, I managed to not screw that up. I am just as amazed as you are, for what it's worth. So we don't have much more time for today. What I intend to do on Wednesday is we're going to work a similar problem, except that we're going to have 2 of the same energy storage element. And I will make one to where the math isn't as hard at the front, the beginning. So anyway, so what to take away from this, for what it's worth, is writing that system of equations or getting that second order differential equation for your system is by far the hardest part of this stuff, okay? Once you get that second order differential equation, everything is the exact same thing that we've been doing. So that is the part that is going to take the most amount of effort / practice and all of that kind of good stuff. For what it's worth, on your exam on Friday, the take-home portion, excuse me, the in-class portion is only going to be series or parallel RLC. This will be take-home test stuff. And it will probably, your take-home test will very likely be one of these questions.